Hi everyone, and welcome to what is actually our last lecture. So I'm sure most of you, or probably all of you, including myself, are happy to hear that. We've made it quite a long way through the course, and now we're coming to the end. And in this lecture, we're going to be looking at the FAST file system, which is a slight optimization on the one that we looked at last week. And the last topic we're going to be covering for this course is crash consistency. So how do we handle cases, or how do we circumvent issues that might arise when like the system crashes or there's a power loss or something like that. So like I mentioned last week, we delved into our first lecture on the file systems as well as like input-output devices and persistence. Now, just a quick summary or takeaway from that was that, well, this file system is like this logical layer that separates our hardware from like our user programs. And this logical layer is provided or set up basically through our virtualization. And we all know that that's the job of our operating system. And we saw that, well, file systems are made up of files and directories. And they're basically implemented as data structures that can be manipulated to, indicate where data is, the names of files, as well as like we learned about special IDs called inodes that basically kept track of where our data was on disk. So we're going to be, I'll start by just like reiterating a few of those things firstly, and then we'll get into our FFS. So this was the diagram that we looked at last week. Now we had this component called the superblock, and that contained information about the entire file system, right? How big the volume is, how many inodes there were. It also pointed to the head of the free list of blocks. So basically containing all the metadata of that disk. Now, the inode region of the disk contained all the inodes for the file system, and these were like our unique identifiers for individual files, which contained pointers to where the data was of that file. And these pointers pointed to, obviously, the largest components of our file system being the data block, where the actual data was. Now, this was the diagram that we saw for our very simple file system. And the positives were that it was simple to implement. It supported our basic abstractions, which were those functions like open, write, read, close. And it was fairly simple to understand and implement and use. Now, the problem with this that we didn't actually really discuss too much about was that its performance was pretty terrible. And that's where the fast file system is going to come into play to try solve this performance issue. So just to demonstrate why the performance was an issue, we're just going to look at this slide quickly. And the main issue was that our old Unix file system that we looked at last week treated the disk like it was random access memory. And that meant that data was spread all over the place without any regard to the fact that the medium that was holding the data was a disk itself. So here's like a diagram of a disk, and the file system that we looked at last week didn't really understand or know anything about like the structure or the layout of this disk. It just utilized it as a single block. Now, why did this result in some performance issues? Well, for example, the data blocks of a file were often very far from each other, or very far from the inode itself as well. So if, say, A1 here was the inode that pointed to a specific data block, and that was over here, and then, say, A2 was the actual data, and that was over here, there is quite a bit of distance that our read-write heads, which are these like little thin guys over here that actually read the data, there's quite a bit of distance that would have to travel before it would read like the next item in, or the next component of that file. And like there are extreme cases where this could arise, even where we had like A1 here and then we had to go read something over here, and it would require the disk turning and the head going up and down along the different tracks. Now, with the way that we generated our file system last week, this was very possible, and it led to cases where obviously very poor performance in terms of our what we call our seek time. Now, seek time is how long it takes the disk to spin as well as the head to move up and along the disk to actually get to the specific like spot on the disk where the data is stored. So it was poor in terms of our seek time. Now, and even additionally, there was an issue that arose, is that the file system would end up getting very fragmented as the free space was not carefully managed at all. So there's a little example here with 4 different files of this occurring. So we have here multiple files A, B, C, and D, all nicely laid out next to each other, and you could assume that, well, A1 was generated, A was generated, then B was generated, C and D, and they just slotted in nicely next to each other. But then, well, what happens when B and D is deleted? And now we have like these 3 regions separated by these 2 files. And then maybe another 5th file was created, and this was like a larger file, and it would have to be spread across multiple blocks, separated by other files. Now, this was also a case where fragmentation, or this is a case of fragmentation, and you can see this is not necessarily ideal. Now, the result was that our logically continuous files, or contiguous files, would be accessed by going backwards and forth across the disk, across multiple different regions, and this reduced the performance quite substantially. A third slightly smaller problem, or easier one to fix, was that the original block sizes were too small, and they were only 512 bytes, these individual blocks. However, that was easily rectified by just increasing the block size, so that's not a big one to solve. But the other 2 issues were thankfully solved with this idea that they developed, or this team at Berkeley developed, and that was called the FOST file system. And their goal was to design a file system which utilized an allocation policy to the disk where it was disk aware. And that was in order to improve performance. Now, what do I mean by disk aware? Well, they wanted to take into consideration the structure and layout of the physical disk. So where things was important to where files should be stored and allocated. So where they were physically on the disk. And they also wanted to keep the same API, so like the open, read, write, and close functions. All they wanted to do is basically change the internal implementation of the file system. And that's what they did. So how it works is that our FFS divides the disk into a number of cylinders, or a bunch of groups called cylinder groups. Now, a single cylinder is a set of tracks on different surfaces of a hard drive that are the same distance from the center. So it's a set of tracks. So these like rings are what we call tracks. And it's a set of them that are the same distance away from the center. So what you can see here is that all these like gray rings would be on the same group. And then all like the lighter shade, or the different colored grays would be on their own group. So the blacks on their own group, this light gray, their own group, this lighter gray, their own group, and this like darker gray is their own cylinder group. So that is how they divided their disk up. And the idea here was that these groups were used to improve our seek performance, like I said. And how that worked was, well, by placing 2 files within the same group, that means they must be closer to each other. So accessing one after the other will not take as long to move the head across the disk. And FFS needs to allocate files and directories within each of these groups. So this is an important thing here. What that means is that we have to change our structure up a little bit. So once again, like I mentioned, by placing files within the same group, we can improve our performance, right? But to use these groups to store files and directories, our fast file system needs to have the ability to place directories and files into a group. And therefore, because we need to be able to do this, we need a way of tracking all the necessary information about everything within an individual group. So if you remember, we had this data structure here with our superblock, our bitmaps, our inodes, and our data. Well, how it works with the fast file system is that we just have one of these for each group. So to do so, FFS includes all the structures you might expect a file system to have within each group. And then they'll have a way of referencing each of those groups. Well, with this now group structure in place, the question becomes how to decide how to place files and directories as well as their associated metadata on the disk to improve its performance. So the question, how to allocate our files, right? Now, they utilized, or they had like this design mantra that was quite simple, and that was that keep related stuff together. And to obey this mantra, FFS decided that, or decides what is related. So what do I mean by related? So the idea here is that it wants to place related, stuff that is related within the same block, and conversely, unrelated items should be placed into different blocks. And to do this, they made use of a couple different heuristics. And a heuristic is just like a metric that you can use to measure performance. So let's look at the first idea, or the first part of allocating files and directories, and we're going to look at directories first. So FFS employs a simple approach, right? We find the cylinder group with a low number of allocated directories and a high number of free nodes. So we want to find a group that is relatively free. And once we found that, or once we found the group that performs highest with that metric, we're going to put the directory data and the inode in that group. Okay, so we look for like the least occupied group, and we put the data and the inode in that group. Now the second, for files, FFS does two things. First is make sure in a general case to allocate the data, so the data blocks of a file in the same group as its inode. So that's in general. We want to try allocate data in the same group as its inode. And this hopefully prevents long seek time between the inode and the data itself, which could have been the case in our old file system. The second condition is that it places all files that are in the same directory in the same cylinder group of that directory. So here's an example of a couple different files in a couple different directories. We have this file B in our directory A, as well as C and D. These are all three in the same directory, right? And B, well, the file F is in directory B. So if the user creates these four files, B, C, D, and F, FFS would try to place the first three near one another or in the same group, and the fourth one, which is this F file, in some other group. Okay. So that is how FFS handles the allocation of files and directories. Now there is one exception to this, and that is for large files. So this is one important exception to our general policy for file placement, and that arises, like I said, in the cases of very large or large files. Now, without a different rule, a large file could entirely fill a block, and that's what you can see here. Like we have this block G, G2, and it's been completely filled by some file data here, hypothetically. And filling a block in this manner is undesirable as it prevents subsequent related files, so like files within the same directory, from being placed within this block group, and this might hurt our file access times or the locality. Okay, so how do we solve this? Well, what we do for large files is that we spread them across a disk in what we call chunks. So we divide them up into chunks, and we put each chunk on a separate block, or in a separate group. Now this hurts performance, but because now you have to look at lots of different groups. But if you increase or decrease your chunk size, obviously you can optimize this for different scenarios. The idea here is that, well, we are reducing our performance in this case for the specific file, but overall when we're referencing or loading and writing and reading from lots of different files within maybe the similar groups, then our performance is actually increased in that case. So short term, yeah, for this file, performance is decreased, but overall performance for all files is increased. And that's what we mean by this amortization. So thus, for large files, FFS does the following. After some number of blocks are allocated in the first block group, that is our chunk size, FFS places the next large chunk of the file, and these are basically those pointed to by the first indirect pointer. So our direct pointers would be pointing to data within the same block group, and then our indirect pointer would be pointing to data that would be stored in another group. And then the next chunk is basically points to another block or another group, and then the next chunk would point to another group, and so on and so on and so on. So that's how FFS handles our large files. Not too complicated, just separate them over multiple groups. Cool. So that's the first topic today is our FFS. And the second one is going to be crash consistency. And most of the second part, or part 2's lecture, will be focusing on two types of, or two approaches to handling crash consistency. So unlike most data structures, like memory and address space and all that type of stuff, our file system data structures must persist. So they must survive over the long haul or after power loss, as well as over a longer period of time, i.e. like they say here, stored on devices that retain data despite power loss. And one major challenge faced by a file system is how to update persistent data structures despite the presence of a power loss or system crash. So here what we're saying is, well, what happens if right in the middle of updating those on-disk structures, so like our inodes or the data block, our bitmaps as well, what if the power loss? What if something trips, right? Or perhaps even the operating system encounters a bug and crashes. What happens in those cases? Well, we'll begin by, like I said, examining the approach taken by older file systems, and that is our file system checker, as well as journaling. And journaling is still relatively used today. But let's get into a couple examples of when a crash can occur. Okay, so our example that we're going to be dealing with is when we want to append some data, a single block of data to an existing file. So in order to do this, we have to open the file, obviously. We call lseek, which moves the file offset to the end of the file. We call, then we issue the write command for 4 kilobytes, and after which we then close the file. Okay, so let's also just assume a couple things here that I'm going to talk about. Let's just assume that we're using that standard simple file system that we looked at last week. And this tiny example is going to include our inode bitmap that only has 8 bits, 1 per inode. A data bitmap which also only has 8 bits, and that's 1 per data block. We're going to have our inodes, obviously, and that's, like I said, 8 of them, numbered 0 to 7, so this would be 0 here. And our data block also with 8s numbered from 0 to 7, and this is 0, 1, 2, 3, 4, 5, 6, 7, like that. So if you are to look at the structures in this picture, you can see what I'm talking about. And we have a single inode, which is allocated at inode number 2, so it's 0, 1, 2. Okay. And you can see this is marked in our inode bitmap over here, as well as we have a single data block, which is also marked in our data bitmap over here. All right. And this just, for brevity's sake, we're just going to be calling this inode v1 because we're going to update it, and then you can see then it'll be called v2. But that's just in general how our example is going to work. So this is what it looks like before we append a single data block. Cool. So if we had to then look at this simplified inode, we can see some statistics about it or some data. We know that its size of the file is 1 because it has one block allocated, right? It's just this one data block here. The file, the first direct pointer points to block 4, and we can see that here. And this is again 0, 1, 2, 3, and 4. And this is labeled DA. And all the 3 other direct pointers are set to null, all right, because they haven't been allocated. They're just set to null. Now, when we append to the file, we are adding a new data block to it, and thus we must update 3 on-disk structures, right? The inode, all right, because we have to update this here, which must point to the new block and record a new larger size due to the append. The new data block itself, right, which we'll call DB, and a new version of the data bitmap, because that has to also indicate that a new block has been allocated. So again, this is what it looks like before. We know what needs to be done. So what does it look like after? Cool. So this is now after the update. And now in our memory, in the memory of the system, we have 3 blocks which we must write to the disk. The updated inode, and you can see that there. And that's like inode v2, just so you know that's the version 2. And it now looks like this. It has pointer, the first pointer pointing to 4, the second pointer pointing to 5, and you can see the size now has changed to 2, which makes sense again. We can see the updated bitmap here with this bitmap version 2, which has now another allocated block in it. And we can see that there is now an additional data block, which is DB, which is just filled in wherever it means allocated. Nothing really important there. But this would be what it would look like afterwards. So to achieve this, what had to be done? Well, the system performs 3 separate writes, like I said, right? 1 to each of the inode, the data bitmap, and then the data block itself. Now, like we also discussed at the very end of last week's lecture, these writes don't usually happen immediately. They are stored in like a buffer, so that multiple writes can occur at the same time, so they're stored in memory. And we call it a dirty inode because it hasn't been updated yet, but an update needs to be reflected. Now, the question becomes, well, if a crash happens after one or two of these steps here, but not all 3, the file system could be left in like a funny state, right? There could be an erroneous state that it is left in. So what are some of these conditions? Well, let's just take a couple examples, right? The first one is, imagine only one of those writes succeeds. So only one of these 3 succeed. Thus, there's obviously 3 possible outcomes, right? The first is that just the data block is written to disk. Now, this is not actually a big problem. The data will be written to the disk, but there's no inode that will point to it. And because there's no inode pointing to it, it's as if there's no file or there's no writes that had ever occurred. So all you would have to redo here is basically reperform that write. But it's not like in a bad state, the disk. It's just as if that would never occurred. Now, the second is a little bit more of a problem, and that's if just the updated inode is written to disk. So this inode now will point to the disk address of 5, which was that DB. But an issue here was, well, DB has not been written to this, so there's no data there. So if we had to read that file location, we'll read garbage data. Whatever was the original contents or old contents of the address 5 is what we'll read. And this is what we call a file system inconsistency, or there's an issue here. Now, the third case is obviously that last case that we haven't touched on, is that what if the bitmap is written to disk but nothing else occurs? Well, if that occurs, well, that will indicate that the block 5 is allocated, but there is no inode that points to that. Thus, the file system is inconsistent again, as we have a space leak. That's what this problem is called, a space leak, because block 5 is allocated, but it would never be used by the file system, right? And it wouldn't even be unallocated because there's no inode or file in essence to delete, so it would never be unallocated and never be utilized ever again. So that's obviously another issue. So that's if only one of these occur, but obviously there's the cases where if 2 out of the 3 writes are successful and the last one fails. So in this example number 1 here, the inode and the bitmap are written to disk, but the data fails, or the data isn't written. So the issue arises is that the file system metadata is completely consistent, meaning that, well, we have a file that points to some location, so that's good. And we know that the location that it's pointing to is a block that has now been allocated or is present in our bitmap. The issue is that, well, whatever it points to, or this block 5, for example, it just has useless or garbage data in it. The second case is when the inode and the data block are written, but they're not the bitmap. So here we have an inode pointing to the correct data on the disk, but there's a problem between the inode and the old version of the bitmap. Now the bitmap might say it's allocated, which would be lucky, but it might also say that it's unallocated, which would then allow it to be allocated for another file, and you could get an inconsistency there. Thirdly, you could have the last case, which is the bitmap and the data block being written, but not the inode. So here we have an inconsistency between the inode and the data bitmap, where we have no idea which file it belongs to. So the block has been allocated, and there's data in that block, but we don't know which file that data actually belongs to, or which file points to that data. So all of these issues are what we call in general the crash consistency problem. And the idea here is that what we would ideally like to perform those 3 writes atomically, meaning that we could shift from a constant state or consistent state to another, or a safe state to another. Unfortunately, we can't perform those writes atomically. And that is because the disk only commits 1 write at a time. And again, because crashes or power losses may occur between these updates. Now, that is going to be the end of part 1, basically just outline the issues that we have to deal with. And in part 2, we're going to be looking at those 2 solutions to our crash consistency problem. Thank you for listening, and I'll see you there.